Welcome to NASA Edge.
An inside and outside look at all things NASA. And today we're going to be talking about the Artemis 1 launch, a very important mission for NASA. We're going to be talking in specific about imaging the Artemis 1 on launch. Later on the show, we're going to be joined by Jennifer Inman and Franklin Fitzgerald to talk even more about this important process.
Blair, we're not talking about our imaging like with the cameras that we have around here. We're talking about professional imaging.
And that brings us to Tom. Tom, we've worked with you for years, but you've been imaging the shuttle for a long time, back in the later aughts, but then you've moved on and grown this technology to image now Artemis. So tell us, what exactly is SciFly?
Well, so SciFly, we're actually going to be implementing a special imaging system on the nose of a high-altitude WB-57 aircraft. It's a special imaging system we call SAMI. This particular instrument is designed to measure the temperatures of the core stage of the rocket during ascent. We won't be able to recover our core stage. It has instrumentation, but it's limited instrumentation. So this is a very unique opportunity for the engineers at Marshall to better understand the environments of the base region of this rocket. This is where all the critical avionics hardware is housed and that control the rocket nozzles during its initial stages of flight. So it's very important we understand how well that avionics are protected.
Now, as I think about SciFly, I'm thinking SciFly, scientifically
calibrated in-flight imaging.
Right, so it is clearly, Chris, all about this important imagery.
But the cool thing about it is you have developed this technology or this capability since, what, 2003, 2004?
Goes back to 2003, Chris. I was involved with the Columbia accident investigation, the return to flight. I was part of a group of engineers that had to use tools that we developed on wind tunnel data here, generated here at Langley, to disposition damage on the shuttle that occurred during launch. So the aerothermodynamic community that I'm involved with, we kind of rallied and advocated for an experiment to be flown on the shuttle. We simulated damage by placing a bump on the underside of the wing. Protuberance in a safe location to better understand the temperature environments during reentry from that localized heating created laminar turbulent flow. But you don't see it with your eyes, but an infrared camera, you can see. Now, we do these kind of things in the wind tunnel all the time. We have, scaled models like this, infrared camera, looking at it optically, 3 feet away. So I asked myself, the challenge here was, could we do the same kind of thing in flight? It represented a paradigm shift. We traditionally collected data with instruments on the vehicle, thermocouples. But could we look, with the orbiter flying, 50 miles away, track it and get a global snapshot.
At high speeds, too.
At high speeds. Don't blink.
I mean, we're talking anywhere from 18 to 24,000 miles an hour?
24,000 miles an hour, yes, sir. So it's very tricky. It's a very tricky process to, track that vehicle, acquire it, track it, and maintain it in the narrow field of view and get that temperature image that the engineers were seeking. So we did that successfully, for 7 shuttle flights.
And now you've expanded this capability to not only you can observe vehicles coming in, re-entering the atmosphere, land-based, air-based, and ship-based.
So
right?
yeah, so the photons, they tell us a very unique story. I mean, what we've been talking about here with the shuttle was, infrared imaging for temperature retrieval. But the photons also tell us in the visible spectrum, like with the work we're doing with the Commercial Crew Program, the commercial partners returning their capsules, back from space. The SciFly team was an integral part of that development and validation process associated with those parachute recovery systems. In that case, aircraft and ground systems were used simultaneously to obtain the critical data, the health monitoring of these parachutes to make sure that those last phases of entry, descent, and landing, the descent and landing occur as we were expecting.
It's one of the most critical parts of the mission is EDL, right?
Yeah, I mean, you would think in my discipline, I've always had the perception that, the high temperature aspects of reentry were, the critical parts, but actually my understanding now is that, the parachute architecture, that's one of the leading risks. And hence, the agency put a lot of effort to ensure that we had a safe design for those commercial systems.
I think what's interesting is that what you did back with the shuttle program, with the imaging on the protuberance, that whole process, you learned a lot. And then now, because of the good data, because of what you discovered has now found a place in almost all aspects of launch and landing.
We support multiple mission directors, actually, and we've been talking a lot here about the human exploration side. Right. But we've also supported a lot of planetary science missions, so things coming back from, asteroids, the heliophysics, launches from Wallops that we've supported with optical imaging. So it's really, the team has really broadened its base in terms of, going from just initially supporting thermal imaging, and now it's, pretty extreme range of capability that we've developed for the agency.
Tom, you've built quite a team. In fact, we're going to be talking to Jennifer later on in the show. Thanks for being here. We did have a chance, however, to travel to Houston, Texas to talk to the team developing the SAMI instrument for SciFly and getting it ready for the Artemis launch.
So Matthew, we're here at one of the labs at Ellington Field, and the star of our show, SAMI, is directly behind you. Can you tell us what does SAMI stand for?
So SAMI stands for the SciFly Airborne Multispectral Imager.
And what will this instrument do?
So this is an imaging payload that measures different wavebands of light, some bands that we can see, some bands that we can't, in order to try to obtain scientific imagery for launches and reentry missions, in addition to other support that we may provide for NASA commercial crew program.
So SAMI is being used with the WB-57. Why is it being used with that airborne platform?
So the WB-57 is an airborne asset that we actually use quite often for both launches and re-entry imaging missions. The reason that we do that is because it is a high elevation asset, meaning that we can get higher above more clouds than most of the other aircraft that we have access to. In addition to that, we have a breadth of knowledge of conducting these airborne missions with the WB-57. We have a lot of support through both NASA and some contracting companies that were able to help us develop the system. And really, it was the most difficult environment that we could have developed this in. So moving on from here, we'll be able to apply it to, different aircraft, even put it on the ground or even on a boat in the ocean to collect imagery.
So how will SAMI be operated during the Artemis launch?
So for the Artemis launch, the SAMI payload, which is what we call the whole system with all the imagers inside, will be placed inside of a ball turret on the nose of the WB-57, which has 2 rotational degrees of freedom, which will allow us to point it at the Artemis as it launches, and it will be operated from the rear seat of the jet. The person in that seat we call the Special Equipment Operator, the SEO.
Prior to SAMI, you had a similar instrument called Dynamite. How different is SAMI from that instrument?
So the Dynamite payload consists of 2 imagers, one visible and one mid-wave infrared. Both of them are capable of zooming in from very close to very far away. And the difference between that and SAMI is SAMI actually has 6 different cameras on board, 4 of which are a constant field of view, constant zoom. And the other 2 are wide to narrow zoom cameras that allow the SEO to accurately and quickly acquire and track any object that we wish to view through the camera.
Now, acquiring and tracking the rocket or capsule for a launch or reentry is totally different. Can you tell us about that procedure?
Yeah, so for launches, obviously the rocket is sitting on the ground right before it takes off. So as the WB actually approaches its planned flight path, the WB can acquire the rocket on the pad and continuously track it as it launches off of the ground. So the initial acquisition of the target is actually is much more simple than a reentry mission, because in a reentry mission, you actually have to find a much smaller vehicle in the sky as it's coming toward you, or as it were traveling across the sky at a much greater rate of speed. It's much smaller, much further away than for launch missions. So what we tend to do is we actually give them what's called a horizon break, which gives the first point in time when the WB should actually be able to see the capsule as it comes across the horizon. And that way they can point in that direction with a wide field of view, acquire that, and then zoom in with that to punch in the narrow field of view sensors.
So SAMI will be used to image the Artemis launch and re-entry. But beyond that, what are the plans for SAMI?
So SAMI was designed to be a very flexible imaging asset. Because of its unique capability for multispectral imagery, we've actually designed it in such a way that we can install it on a wide variety of NASA assets. Ideally, what we would like to do is develop the interface to install the SAMI system onto one of the Gulfstream aircraft and take it with us to image the OSIRIS-REx mission that's upcoming in our schedule. This is a very unique opportunity due to the high heating rates that we'll have, and we'll actually be adding some future capability to SAMI to do that.
Very interesting information on SAMI, but right now we'll learn a little bit more about SAMI and SciFly from our next guest, who is Dr. Jennifer Inman. Jennifer, can you tell us about your role as a project manager and the other assets you have in SciFly?
Absolutely, it's nice to be here with you guys today. We're really excited for Artemis launch, and we're going to be there with all of our bells and whistles. We've got 2 ground-based imaging systems that will be on the Cape at Kennedy Space Center, imaging the launch, and we'll have an aircraft, the WB-57 that you've heard about, flying during launch, and we'll also have SAMI on the WB-57 when Orion returns at the end of the mission.
Pretty complex stuff you guys have going on here. But one of the things I'm wondering is, when we talk about data, because we often talk about collecting data and gathering lots of data on any given event or during a launch or something like that, what exactly is the data that you guys will be getting that's so important during Artemis 1?
Oh, I like questions like this. On our team, we like to talk about how it's important to actually get information rather than data. If you get data but no information, then you've just filled up hard drives. So the type of information that we're trying to get here directly addresses some of the requirements and the science requirements for launch and some of the engineering requirements to certify the SLS system and the Orion capsule for human spaceflight. So some of the questions that we'd like to answer are whether the separation dynamics with the solid rocket boosters are as we expect them to be. We'll get that from our high-resolution airborne imagery. We also are looking to answer questions about the thermal protection system and to see what types of temperatures are achieved on the vehicle. So one of the temperatures we'll be looking at is the temperature of the outside of the core stage of the rocket. There's a phenomenon called plume-induced flow separation, where you get a shock wave ahead of the rocket plumes that can cause hot exhaust gases to be entrained in the boundary layer flow and creep up along the sides of the vehicle. So we'll be looking at what temperatures are achieved there on the outside of the vehicle. We'll also be looking at the core stage, at the base of the core stage. So SLS has 4 rocket motors, and we'll be looking at the region between those 4 rocket motors to see what types of temperatures you get when the hot exhaust gases are entrained into the flow at high altitudes where the pressure is lower. And so we want to see whether the thermal protection material that we have in that region is adequate, or even if it's more than adequate and we can shave some weight off for follow-on flights.
Well, it's interesting because obviously SLS will have some kind of internal sensors itself collecting some of this data. Are you guys targeting gaps, or are you working together with them on maybe where they could use some more data? How does that work?
Oh, really good question. We definitely see our off-body measurements as complementary to the onboard instrumentation. So onboard instrumentation on the surface of the vehicle gives you discrete measurements over the full flight profile. We'll be getting global measurements over a more reduced set of the flight profile. Every pixel of our thermal imaging basically acts like a thermocouple in that location where we can measure what the surface temperature is. We're also subject to very different failure modes from onboard instrumentation. So, we might fail to acquire data, as an example, if something happens mechanically with the aircraft that causes it to return to base or not be able to take off in the first place, or if clouds block our view of the rocket at some point during the trajectory. On the other hand, onboard instrumentation can have different failure modes due to electronic failures or things like that. So they definitely go hand in hand, and we can independently measure the same variable that we're interested in and see what answer we get from the onboard instrumentation and what answer we get from the offboard instrumentation and make sure that they agree.
That helps you kind of calibrate either way, right?
Absolutely, yeah.
Now, you talk about the onboard instrumentation. Is there any redundancy between the WB-57 and your ground-based assets?
For this particular mission, we are not getting calibrated thermal imagery from our ground-based assets. That's something that requires additional funding that we weren't able to secure this time around. But we are able to get really high resolution imagery from our ground-based assets, because you can use larger optics. And so the types of quantitative information we can get are related to subsystem performance. We can look at the timing of events, and we can see details of things that happen. We can also, if anything anomalous happens, we'll have high resolution, high-speed imagery to see what happened there. And we have different views. We have 2 ground-based imaging systems, and we have the airborne system, and they'll all be looking at the rocket from different perspectives. So that way we'll be able to see what happens to components like the solid rocket boosters from 3 different perspectives.
It's funny, everybody's excited about seeing the Artemis launch. Even your assets are like competing for space to image the launch. It's very exciting. Yeah. In fact, we had a chance to actually talk with the crew of the WB-57 as they prepare to image the Artemis on launch. Let's check it out. DJ, as pilot for the WB-57, you fly a couple of different kinds of missions for SciFly. You cover rocket launches and reentries. Can you tell us a little bit about the challenges for a rocket launch?
Yeah, both have their own unique challenges, but I'll tell you, from the pilot perspective, it really comes down to putting the aircraft in the right spot at the right time, because they both have very specific timing requirements for the sensor equipment operator.
Now, I've seen a few launches, and I've noticed that they don't always happen at the exact time. So what do you do when you find yourself in one of those situations where there's a hold or there's a delay or something, and yet you still want to be in position to get the imagery?
Yeah, that can definitely present a challenge for us. And what we do is we have a bunch of different ways that we can solve that timing problem by extending our holding pattern, shortening up our holding pattern, working airspeed. So we use all of those tools in order to try and, like I said, get that aircraft back in the right spot at the right time.
Tony, DJ told us about the challenges he has of putting the WB-57 in the right spot. What are your challenges as operator for SAMI?
Well, my challenges start from the time it was being developed and getting to know the system. But then in the flight environment, I've got to worry about the focus, the framing of the image, and then tracking the actual object itself. So you've got to handle all of those things at the same time while maintaining situational awareness, and if anything comes up that you have to then adjust to.
And of course, in a rocket launch in particular, you start knowing exactly where it is, but then it moves pretty rapidly. What's that process like tracking a moving object at that speed?
Well, one of the good tools that we do have for this is we've got a trajectory that's the nominal path of the rocket, and that helps guide us. So if we do lose it in the clouds for a little bit before it gets up above those, then they can keep us in the right vicinity. I know where to be looking, and it goes from there.
So I imagine that you're in communication with the ground quite a bit ahead of the launches and reentries, but also throughout the whole mission. Can you tell us about that?
Yeah, absolutely. Throughout the entire process, we have our own designated Capcom, and those folks will go ahead and let us know how the countdown is progressing. If they're anticipating a hold, we can start to work the timing problem early, because as a jet aircraft, we can't just hover, and we have to keep moving and, again, get the aircraft back there when it's time to push.
Now, there are also challenges on reentry. We had someone describe it as if you were looking through a straw trying to track an object in the distance. Tell us a little bit about how you acquire these objects as they're coming in at very high rates of speed.
Well, we start out with a wide straw, and then we use a more narrow straw later. The greatest thing we have for the reentries is the mid-wave infrared, which is just all about the heat and the signature there. It stands out against the cool night sky very well. And so we use that, we use a wider field of view, and then we zoom our cameras in to get the scientific grade imagery. By the time it gets closer to us, it winds up being about 5.5, 6 miles away when the key stuff happens, as opposed to 1,000 miles away when it comes over the horizon.
And of course, that's a little bit more challenging because it's coming from outer space. And it's a little, I know you have some information, but are you all nervous trying to make sure you get it right when it's visible to the human eye, or to Sammy's eye in particular?
Only every time.
Yeah.
Yes.
Safety is also a big priority, and you're flying during very dangerous activities. And so tell us a little bit about what's required for you guys in terms of safety.
Yeah, the big thing with the safety is that all is part of our mission planning process. We work with the experts to make sure that we stay out of the hazard zone if something were to go wrong during the launch or a reentry also. We make sure we keep the aircraft out of that hazard zone. And again, we're also in communication with the ground. And if they see something going wrong, then we can make sure we turn the aircraft out of the way to keep ourselves safe.
How do you test something like SAMI? Because the opportunities for launch and reentry are so rare, you got to be on your A game. So how do you prepare to nail it each time?
Well, for launches, we are looking at some targets of opportunity, some other launches happening in the area or on the Cape that we can go and image as part of the training process. For reentries, that's pretty much a one and done. Nobody wants you to go and practice against their reentry, especially if it's an operational mission with a developmental payload. So we've really got to develop the tools that we've learned in other payloads, like the dynamite payload, and we're going to use those same tools and techniques against SAMI, and we know which benchmarks to expect before we say, all right, SAMI's ready for that job.
Now, Artemis 1, pretty special. And I know you fly a lot of missions, but how does it feel to be part of NASA's return to the moon?
Yeah, it feels awesome to be a part of that. And the biggest thing is we never take a rocket launch for granted, and we always know we have the best seat in the house. And again, it's an awesome experience, yeah.
It seems like one of the big challenges for SciFly and anybody studying these kinds of operations is the fact that you don't really get practice. This is a one-time opportunity, but it seems like each opportunity is very unique. How much data do you have to compare with on something like an Orion reentry?
Well, you certainly hit a nail on the head there. We like to say there are no do-overs in spaceflight. Or one of our providers says, every day is Super Bowl Sunday. And so the real key is planning. We do a lot of planning ahead of time. We do a lot of simulations where we walk through timelines and we practice the call-outs that we're going to make, and we practice adjusting our trajectories, if the deorbit burn happens a little bit differently than expected. So a lot of this is planning ahead of time, knowing where the aircraft needs to be, knowing what to do if the trajectory of the capsule changes in real time. We do a lot of simulations as well on what we expect to see. So we take a model of the vehicle and we put it into a 3D rendering environment, and we model our sensor system as well. And we model things like the temperature of the vehicle and the number of photons you expect to be emitted based on the emissivity and the material properties of the surface. And all of this tells us what sensor settings we should have ahead of time, because you don't get to adjust your exposure time in real time. So if you have the exposure time too long, it could be saturated or underexposed, you're just not getting enough light. So we simulate an end-to-end mission in order to maximize our potential for success.
Do you feel any pressure?
Absolutely. There's definitely a game day feeling that's energizing and requires a great deal of focus. It's kind of a different level of consciousness that you operate in when you've got your astronaut socks on. That's my game day tradition, is to wear my astronaut socks. And you get your game face on and get focused on the mission at hand.
Well, we want to wish your team the best during launch and recovery, and just thanks so much for being on the show today.
Oh, it's been great. Thank you so much, Blair, Lincoln.
You're watching NASA Edge.
An inside and outside look at all things NASA.